Now, one type of gravimetry which is a little counterintuitive is what is known as volatilization gravimetry. So far whenever we think of gravimetry, we have been thinking of a precipitate being generated and the precipitate being separated under gravity, weighed, and then the analyte concentration evaluated using the amount of precipitate that is being generated. In volatilization gravimetry, completely inverse protocol is followed. That is, the reaction between the analyte and the reagent. So, analyte plus reagent generates a volatile species. And this volatile species is then quantified to gauge or to measure the amount of analyte that is present in our sample. Let us take a very quick example of such a volatilization gravimetry. This can be used very well in quantifying the amount of, say, sodium bicarbonate or baking soda in antacid tablets. So, what we do is we take the antacid tablet containing the sodium bicarbonate and react it with an acid, say hydrogen chloride or hydrochloric acid, and this generates carbon dioxide. Now, this carbon dioxide is the volatile product of this gravimetry, which can be quantified, and quantification of the carbon dioxide that is being generated in this reaction mixture will lead us to the amount of sodium bicarbonate present in the antacid tablets. So, how do we achieve this? We pass this carbon dioxide into a sodium hydroxide solution which is pre-weighed, and this generates sodium carbonate and water. The sodium carbonate can be analyzed by various analytical techniques to quantify the amount of carbon dioxide that is being generated. So, it is also very important to note here that this absorption of carbon dioxide by sodium hydroxide is also happening naturally when we keep sodium hydroxide beads or sodium hydroxide solutions exposed to atmospheric air. So, the sodium hydroxide solution or the beads will absorb atmospheric carbon dioxide and give rise to the formation of sodium carbonate. So, that is also one reason why sodium hydroxide is not considered a primary standard, because its stoichiometry or its composition undergoes change on exposure to the atmosphere, either in terms of absorbing moisture or in terms of undergoing a chemical reaction with the atmospheric carbon dioxide to generate sodium carbonate. So, in the last part of this class, we will be considering how precipitation gravimetry is undertaken for quantifying various analytes such as silver ions present in our solution. So, this titration is also very similar to the acid base titration, in that we have the silver ions undergoing reaction with either the thiocyanate or the chloride ions or the bromide anions, and this is an equilibrium reaction where we have the formation of either silver thiocyanate, silver chloride or silver bromide. Now, since it is an equilibrium reaction, all of these reactions are having an equilibrium constant for each of these. For example, for silver iodide formation, the solubility product is what we will use here is quite low, as 10 to the power of minus 17. Similarly, for silver bromide, the solubility product is a little higher at 10 to the power of minus 13. For silver chloride, which is what we usually use when we are testing the purity of our distilled water, we see the solubility product as 1.8 into 10 to the power of minus 10. So, as we do in titration, what we can do here is we can plot the P function here. In this case, it would be the P value of the Ag ions with the amount of silver nitrate that is being added to the solution containing the respective anion. And since it is a PAG value, the value will decrease as the silver concentration increases. So, this has to be written carefully. As the silver ion concentrations increase in the medium, the PAG value decreases. So, what we observed, quite analogous to the acidity constants of the acids, is that the PAG value undergoes the most prominent change when we are talking a KSP value of 10 to the power of minus 17, which is for the iodide anions. When the anion is changed to bromide, the profile becomes less sharp because bromide has a KSP value of the order of 10 to the power of minus 13, and as the KSP value decreases further for chloride ions, this becomes even less sharp, and here the KSP value was of the order of 10 to the power of minus 10. For something like bromate anions, this difference is so negligible that we will see very significant titration errors if we were to titrate the bromate anions, because the KSP value here is of the order of 10 to the power of minus 5. So, what we observe here is that the KSP is in this case analogous to the Ka value in the case of acids, and we require the lower the KSP value, the sharper will be the transition during the titration. So, let us quickly take an an example where we titrate 50 ml of 0.05 molar sodium chloride with 0.1 molar silver nitrate solution. So, we will be adding silver nitrate to the sodium chloride solution and seeing the formation of silver chloride and any residual silver ions concentration will be plotted henceforth. And just to remind, this has a KSP value of 1.82 into 10 power of minus 10. So, let us take an example where at the pre-equilibrium condition or pre-equivalence condition, we have added 10.00 ml of silver nitrate to the sodium chloride solution. Now, our concentration of sodium chloride will thus become the original concentration minus the amount of silver nitrate that has been added here divided by the total volume of the medium now, which is 50 ml original plus 10 ml added silver nitrate, and this will bring the sodium chloride concentration as 0.025 molar, and from here we should be able to calculate the silver ion concentration in the medium by plugging in this value in the solubility product equation, and we get the silver ion concentration as KSP divided by the chloride ion concentration. The KSP value is 1.82 into 10 power of minus 10. The chloride concentration from the NaCl that is remaining is 0.025, and this solves out to be 7.28 into 10 power of minus 9 molar. Now, this can be represented in terms of the PAG plus value, and which is nothing but the negative log of 7.28 into 10 power of minus 9 solving to 8.14. So, initially when we have added 10 ml of silver nitrate, we have a PAG value of 8.14. Now, at equivalence point, we will have the total amount of silver ions that have been added as equal to the total amount of the chloride ion present in the medium, and we know that the KSP is nothing but Ag plus ion concentration into chloride ion concentration, which solves out to be so the Ag plus concentration at equivalence point is nothing but the square root of the K solubility product, and that is nothing but square root of 1.82 into 10 power of minus 10 or 1.35 into 10 power of minus 5 molar. Now, this can be represented in terms of the PAG plus value of 4.87. So, as we see that at equivalence point, which comes at 25.00 ml of silver nitrate addition, the PAG value is 4.87. However, till 10 ml of silver nitrate addition in the previous case, the PAG value was 8.14. So, we will see that as we keep adding more and more silver nitrate, the PAG value will undergo significant reduction. Let us see what is the PAG value beyond equivalence point. What we observe is, suppose we add 26.00 ml of silver nitrate. In that case, we have a little excess of silver nitrate. So, that excess of silver nitrate can be calculated by the total silver nitrate present in the medium minus the initial chloride ions present in the medium divided by the total volume of the medium now, and this solves out to a PAG value of 2.88. So, what we see is that from the initial phase where our PAG value was 8.14, at equivalence point this reduced to 4.87, and just after the equivalence point it reduced even further to 2.88. So, this can again be plotted into a titration curve. A theoretical titration curve can be generated from such calculation. Now, you would have also encountered that hydrogen sulfide is a commonly used precipitating agent, especially when we are trying to do our chemical analysis, and we will understand today why hydrogen sulfide is used commonly as a precipitating agent, and the answer to this lies in the two equilibria that exist here. So, hydrogen sulfide being a weak acid will donate its proton to water as the first equilibrium, and in the second equilibrium we can also expect that the hydrogen sulfide will convert into, we can expect that the monosulfide anion will convert into sulfide dianion. And since these are equilibria, they can be explained in terms of equilibrium constants. So, let us call this as K1, and this is of the order of 10 to the power of minus 7. The second dissociation becomes much more difficult, and this value is almost 10 to the power of minus 14. So, what we see here is that K1 can be defined as the H3O plus concentration into HS minus concentration divided by the H2S concentration. And typically, based on the equilibria that we just mentioned, is that the HS minus, the monoanion concentration, is significantly greater than the dianion concentration. And what we can write is that at equilibrium we will have the H2S present, the HS minus present, and the sulfide ion in a very small amount present at equilibrium. Now, presume that we are dealing with a 0.1 molar H2S solution. What we observe is that the equilibrium concentration of H2S and HS minus is now equal to 0.1 molar. Considering negligible amount of sulfide ions are present. Okay, now what we can observe here is that the H2S concentration at equilibrium will be the original concentration of H2S, which was 0.1 molar, minus the HS minus concentration, and if we plug it in our K1 equation, what we observe is K1 is equal to HS minus into H3O plus divided by H2S, and this solves to the K1 value being known, the HS minus concentration needs to be calculated, and we will also presume that the equilibrium is the only source for the H3O plus ions. Now, when we solve this, we get the HS minus ion concentration under these conditions as 1.0. But what is more relevant for our discussion is that the HS minus and S2 minus concentrations are highly pH dependent. So, based on the pH of the medium, the concentration of these two can be precisely controlled, and this is actually what is being exploited when we are undertaking precipitation of metal ions using H2S gas as a precipitating agent. So, you can keep this in mind when you are undertaking your chemical analysis using H2S gas. And how is H2S gas generated? You must be aware that you have a Kip separators where iron sulfide is reacted with hydrogen chloride uh, to generate the H2S gas, and this can be controlled based on the addition of HCl into the FES is controlled based on how much H2S is being released in the Kip separators. So, this brings us to the end of this week's lecture, where we have seen how calculations can be undertaken when titrations are being performed to calculate the theoretical values of the pH that can be expected in the medium. We also saw how indicators are to be employed, and the choice of indicator will depend upon what is the pH value at the equivalence point. We also understood that the pH at equivalence point is 7.00 only when we are dealing with strong acid and the strong base. If the base is strong and the acid is weak, the pH at equivalence point will be greater than 7. If the acid is strong and the base is weak, the acid will dominate and the pH at the equivalence point will be less than 7. And then we delved upon how we utilize precipitation gravimetry and what are the principles involved when particles are forming in precipitation gravimetry. Finally, we did a quick calculation of the silver ion concentrations when sodium chloride was being titrated with silver nitrate. We figured out that the solubility product is in some senses analogous to the dissociation constant in acid base titrations, and then we saw ultimately that hydrogen sulfide is a very versatile reagent for precipitation, because we can generate it at different rates by utilizing either thiourea or thioacetamide, and we can also control the dissociation very carefully by control of the pH of the medium. So, this brings us to the end of this week's lectures. We will see you next week.